Okay, so far in the first video we have seen how we can use different tactics to get missing informations in real life scenarios when we have to solve problems in real life. And then in the second practice problem, or the second practice problem solution, we saw how we can use the readily available tools or the search engines to get some information that we require to solve a problem on our own. And in the second problem, we also discussed that here for the second problem, we had considered that the building actually has the same floor height throughout all of its floors, but it might not be the case always. So in that case, there are ways to calculate the height of a building properly, and we can go about that. Or if we don't have that special equipment that can do that for you, what are the alternatives? And that is something we're going to be looking at in this practice problem 3, or the practice problem 3 solution, whatever you want to call it. But before we go on to seeing how we can do it on our own without the help of any special equipment and to a level of certain accuracy, we're going to see what the special equipment I'm talking about and how that equipment is used to calculate building heights or heights of different structures. Okay, so here in this Word document that I actually wanted to include in the book and later decided that it's not going to go in the book, actually is showing you how to calculate the height of a building using the proper equipment, which is called a theodolite. And here you can see that the image is for a scenario where the base of the theodolite is not aligned with the base of the building. But the example problem here I have provided for a simple read and to understand. Actually, in that sample problem, the base level for the building, the ground level of the building as well as the ground level of the theodolite is in alignment. Okay. So here I've listed out materials needed and then steps on how to calculate the height. Okay, there you go. You can pause the video and read it out if you want. Right, and then here we have an example calculation. Okay, but this isn't something that we're going to be using because we don't have that equipment at hand. If you're doing an official business, if you're on official business, then you might have that equipment at hand, but I doubt many of us can afford that equipment for self projects or just to, check out if you can apply what you have learned to the things around you. Alright, in that case, we're going to use a different concept, but I want you to read it out, understand how a theodolite is used to better understand the concept I'm going to go over. So if you don't know how this works, just pause the video wherever necessary and read the information that is being shown on your screen. Once you understand it, then again, play the video and move on from there. Okay. And considering that you have read the content above, I'm going to start from here. So we're going to be using the concept of scale, okay, to calculate the missing dimensions here. And I'm going to quickly show you how we're going to do that. But before, if you want to know about what the concept of scale is, you can read it out here. And also, since we're using a photo, it is closely related to photogrammetry. Okay, so you can read it out as well if you want. The information is given here. I'm just going to take you to the summary. The summary of it is that scale ensures that the drawings represent the real world dimensions of objects accurately, whether the objects are depicted at full size, reduced, or enlarged. Okay, so keeping that in mind, we're going to go over to our problem. There you go. Okay, so this is the problem, and from the first practice problem, we already know how we can calculate the base height. So here you can see that I have measured my feet height or my shoe height, which actually came out to be pretty close to 1 feet. And since we're doing an approximate calculation here just to learn the process, but I want you to find a pole that is not inclined, that is straight. Maybe take a picture of it with yourself or another object and then try it out and use the accurate measurement. Alright, I'm just smoothing it out for smoother calculations. And it actually quite resembles 1 feet. It's pretty close to 1 feet actually. So that is why I'm considering my feet size to be 1 feet. And it takes me 8.5 steps to go from here to here. Alright, maybe I'll zoom in here. Okay, so as you can see, this is actually a triangle problem. So I have drawn a right angle triangle right over here. And if you want to do it accurately, then this will not be a right angle triangle problem because this pole is inclined. In that case, in the inclined case, you may use your geometry skills to do the accurate calculations, but here we're just here to understand how we can use the tools that we have at our disposal to get the dimensions that we need to carry out the calculations that we want to carry out, to see if we are capable of what we have learned or not. Okay, so that's why we're gonna consider, we're gonna zoom a straight pole. Even though this picture is not showing a straight pole, I wish I had a picture of a straight pole. I'll tell you what, I'll do another one where I take a picture with a straighter pole, and we can go over that, or maybe put it in the next edition of the book, removing this one. All right, so again, let's go back to the main topic. So from here to here, that's 8.5 steps, meaning 8.5 feet. So here I can quickly write down this information. So we just found out one of the dimensions, which is the base height of the triangle. There you go, done. And now we're going to do is apply the concept of scale. What I'm going to do here is I'm going to keep on using PowerPoint. You can use another software if you want. I'm comfortable with it, so I'm using this one, and this is the method I'm going to use. If you want, you can even print out the picture and use a ruler and a pencil to carry out the calculations. Okay, so now we're going to do a little bit of scale work. So I know my height, and if this is the base where I'm standing, the same base as the pole, I'm going to draw a line, let's say that is about my height, and I'm going to try to exclude my hair. We can zoom in even more to make it as accurate as possible, or as accurate as we can. So if I put it right over there, there we go. I think that's about the right height. Yep, keep it like that. Okay, so there we go. Now you can see the height here in the photo. The height of the line is 0.9 inches. Okay, so let me just quickly take note of that here. So 0.9 inches. Let's change the color so you can see. Okay, so the height of this line is 0.9 inches. So my height in the photo is 0.9 inches. But in reality, my height in actuality is actually, okay, not what I want to do. Okay, all right. Okay, so in actuality, my height is actually near 71 inches. So in the photo, 0.9 inches is representing 71 inches. So now we can easily calculate the height of the pole. Let me zoom out. So the reason I put myself in the picture beside the pole is to get a reference height. That way we can apply the concept of scale in drawings or photogrammetry to calculate the height of the pole. Okay, so we are not requiring a theodolite to calculate the height of the pole. We can just use images, and I try to make sure that whoever was taking the picture, the picture was actually taken by my wife. So I asked her to keep the phone as level as possible. Okay, all right. So that's another thing to look out for. All right, now we're going to put in another shape. There we go. It's going to start from the base of that. It's going to go way up till that location. Okay, that looks about right. And if the pole was straight, that would have been the height of the pole, which here in the photo is 3.46 inches. Let me just copy that, 3.46 inches. So 3.46 inches is the height of the pole in the picture. So let's say if 0.9 inches is 71 inches in reality, then how much would be 3.46 inches? So that's pretty simple. We're just going to multiply 3.46 with 71 and then divide it by 0.9. And it comes out to be 272 inches. So here we have 272. There you go, 272 inches. Now if we convert it in feet, if you want to convert it in feet, so we are going to divide it. There's actually some change, so I'll just put that in 0.955. Okay, divided by 12. It's coming out to be 22.75 inches. 22.75 feet. 22.75 feet. There you go. That's the height of the right angle triangle. Now that we have these two information, we can get the angles. We can also get the length of the hypotenuse, which actually is the cable right over here. So you can do all of that with the power of just a simple photo and maybe some software. If you don't have a software, you can print it out, use a ruler and a scale. All right. Okay, so now that we have got this value, I just simply like to check if it is if the value is within range of the acceptable standard length of light poles. All right, just to see if what we're doing is going in the right direction or not. Okay, so for that I actually put down the typical height of lampposts, and this is actually from a ChatGPT search. This is not from a Google search. We emphasized the importance of using the tools available to us in the last video of practice problem 2. So here I'm doing that. So here you can see that for residential areas, it says the typical height is between 8 to 12 feet. That's not where our measurement is, which is 22 feet. And here you can see urban and commercial areas. It is 12 to 20 feet, but taller poles are often used to provide wider light coverage and enhance security and visibility. Alright, so that is also mentioned here. So that is close to 20 feet. We have 22.75 feet. But if we move on, and it says highways and major roads, so it's 25 to 40. It's a little bit more than what we have right now. So we can say, and the area where the picture was taken, you can clearly see where this picture was taken. It says Balmundo Street. You can even do a Google search on Balmundo Street to figure out if it's a residential area or urban and commercial area. And it's I live here, so I'm pretty sure it's not going to be highway or major roads. It's going to be urban and commercial areas, and the limit is set to 12. The typical limit is 12 to 20 feet, but if it's required for lighting purposes, for security and visibility, it can go a little bit more than that, and we have got a little bit more than that, which is 22.75. So I'd say it's safe to say the height that we have calculated is quite accurate. And also remember, the height we are calculating here for the pole is not the actual height of the pole, because we have assumed the pole to be straight, which actually it is not. So if that's not the case, and if we calculate the exact height, then I believe it will be within the range of either 25 feet or 20 feet. Okay, so what we're doing here is we can say that it is quite accurate, or it is going in the right direction if we don't have access to the fancy tools. Alright, now another question that comes to mind is that, hey, this is supposed to be an engineering mechanics book, right? And the practice problems, why the first 3 practice problems are based on simple triangles and measuring dimensions. Why aren't we solving problems? Why aren't we using equations and stuff like that? The answer to that is that because the practice problem chapter or the practical problem chapter deals with practical problems where no one is going to give you the measurements, because in real life, no one's going to give you the measurements. If you want to try out your skills on your own, you don't have anyone to give you the measurements. So if you want to do a practice problem, or if you want to make a practice problem on your own, you need to know how you can use the tools available to you to get the measurements you need to check your skills or your skill set. So that is why the first 3 problems are emphasizing how you can use your thought process, how you can develop your thought process to use whatever you have around you. For example, you're walking, your shoes, to get some measurement. And then the second practice problem is emphasizing that you can use the tools that are readily available to you. You can use a Google search, you can use ChatGPT or any other AI to get the values you need or any information that you're looking for. And then the third problem is actually showing you that you can use other skill sets that may not be related to the topic of the subject matter. For example, photogrammetry does not fall under engineering mechanics, but it does fall under surveying or any other field. So yeah, you can use the knowledge that's available to you to figure out things, and you just need to be, let's say, a little clever, or you need to think about things, or think about how to solve a problem, or how to get the values, how to get the measurements that you need to carry out a problem. So the purpose of the first three problems was to get the engine started, to make you start thinking about things in a different way, because we're so used to getting the information to carry out solution to problems, and it is very bookish, I think. So yeah, to be more practical, to move towards more engineering approaches, I thought the first three practice problems should be based on how to get measurements and how to calculate right angle triangle values, because triangle values are something that we used a lot in example problems, if you recall from the book. And if you have not yet got a copy of the book, please do. The link is going to be in the description. Okay, it's a fun book to read, if I say so myself. Alright, and yeah, the first three problems are done. So from the fourth problem, we're going to be tackling some engineering mechanics problems. So you're going to be happy from the next problem, so onwards. Okay, alright, so that was it. Thank you very much for watching, and I hope you got to learn something new, and I hope you found this interesting. Have a great day.